Hey everybody, Mr. Piercy here, and what we're going to be taking a look at in this video is how to identify the volume of a pyramid or a cone. Now, the volume of a pyramid and a cone are pretty similar to what you would have had to do for volume of a prism or a cylinder. It turns out that as long as a prism and a pyramid, let's say that their bases and their heights are congruent to each other, as long as they have the same base and they have the same height, the volume of the corresponding pyramid would be a third of whatever its prism would be. Same thing with a cone. And that's why we have the volume of a pyramid to be 1/3 of the base times the height, where the capital B represents the area of the pyramid's base and h is the height of the pyramid. Remember that the height has to be the vertex, wherever that is. That's the segment that's perpendicular from that vertex to the base. Now, oftentimes in volume form or in volume problems with pyramids, they don't necessarily give you the height of the figure, and you have to figure out what is the height. And usually, we'll use the slant height of the figure with, say, like the apothem or whatever the length of the side is divided by 2 in some cases, whatever the apothem of the regular polygon base would be. But now that we know that the volume of a pyramid is going to be a third of whatever its equivalent prism would be, let's go ahead and try working out some equations here where we use it. Now, again, in this case, we have an oblique hexagonal prism, pyramid rather, I'm sorry. And again, hexagons being the fact that we can use 30, 60, 90 rules to evaluate a regular hexagon. They're going to be the most common regular polygon that you see. So we want to know what's the volume of this thing. Well, first we need to know what is the area of that hexagon. So we need to know, well, area of hexagon is 1/2 times the apothem times the perimeter. So what's the apothem? In this case, the apothem, if I could select the right tool, would be 2 radical 3. And the perimeter is going to be the number of sides, 6, times the length of each side, which is 4, so the perimeter is 24. So substituting those into the equation for the area of a regular polygon, we get the area, in this case, to be 24 radical 3 inches squared. Well, now that we know that's the area of the base, well, we can substitute that and work out the volume. So the height of the pyramid is 10 inches. So 1/3 times 24 times 10, in this case, would give me 80 radical 3 inches cubed. That would be the exact answer. And otherwise, we would get 138.6 roughly for the area as, or I'm sorry, for the volume as a general or as an approximate value. Now, the one thing that I want to kind of point out here is they're doing this in 2 separate steps. They're finding the area of the base and then substituting it into the equation for the volume. Now, generally what I would do when I would work something like this out, here I'm going to say volume is equal to 1/3 times the base times the height. So in this case, I'm going to say 1/3 times the apothem, or times the area of the polygon, which is 1/2, times the apothem times the number of sides times the length of each side times the height. Well, simplifying here, I can say that the 1/3 times the 1/2, that's 1/6 times the apothem times the number of sides, the length of each side, and the height. So here I can say 1/6 times the apothem, which is my 2 radical 3, times the number of sides, which is 6 in this case. Oops, let me clean that up a bit. 6 times the length of each side, which in this case is 4, times 10. So you could write your equation like that and do it in, and don't have to necessarily do it in 2 separate steps. But you'll still work out to get the same value here. So you can see here the 1/6 and the whole number 6, that's just going to simplify to be 1. So when we multiply our numbers now, the 2 times the 4, that's 8, and the 8 times the 10, that still gives me 80 radical 3 for my volume. So we can do it that way as well. And I forgot to put that in there in case you're wondering what the volume was there. It's just the same approximate value that we got when we multiplied 80 by the square root of 3. So now here we're going to be looking at what's the volume of a cone. Same thing with with the pyramids and prisms. As long as a cone, as long as the base is congruent to a cylinder, and the heights of a cone and a cylinder are the same, then the volume of the corresponding cone will be a third of whatever its cylinder equivalent would be. So 1/3 base times height again. But of course the base in this case is a circle, so it's just pi r squared. So cylinders and cones are usually pretty easy in that aspect, simply because the base is always a circle. It doesn't really change much. So 1/3 times times pi times the radius squared times the height. And again, kind of with what we saw with the pyramid, sometimes they're not going to just give you the height outright. Sometimes you have to use the Pythagorean theorem with the slant height and the radius in order to figure out what the height of the cone would be. But let's take a look and see how we're going to use this thing. So we have two examples here. We have a cone, a right cone and an oblique cone, where they're giving us the radius and the height. So these are pretty straightforward, cut and dry, nothing crazy about them. So we start with the equation, 1/3 pi r squared times the height. Substitute the values for the radius and the height, 9.5 and 16.8 in this case, and then just multiply. Say 1/3 times 9.5 squared times 16.8. That would give you 505.4 pi millimeters squared. That's the exact volume. The approximate volume, multiply that by pi, and it's about 1587.8. So that's how we get the volume for the first one. Now we're looking for the oblique one. Here we're using Cavaliere's principle. Remember that because doesn't matter that it's oblique or not, the cross-sectional areas will still be the same throughout, so we can still use the same volume equation, just like we could use the same surface area equation. But here the radius is 4.5, so 4.5 squared times the height, 12 divided by 3, will give me an exact volume of 81 pi cubic feet, and the approximate value would be about 254.5. So 254.5. Now, at this point here, now we're going to be looking at, if you've recognized whether we're looking at a pyramid or whether we're looking at a cone, sometimes the height is not going to be given to you. And what you will need to do is be able to use some kind of a right triangle in order to be able to figure it out. Well, because we have right triangle somewhere, that means we can use Pythagorean theorem, rules for special right triangles, or what we're seeing in this case, we're seeing trigonometry being used, because they're not giving us the value of the radius. So, but they are giving us the measurement of an acute angle inside of a right triangle made between the radius, the slant height, and the height of the cone. So here, in this case, because of where the angle is located, we know the side opposite of the angle, and we're looking for the side adjacent to the angle, so that tells me I'm going to use tangent. So again, making sure your calculators are set for degrees and not radians. We solve for here, substituting, the opposite side is 12, the adjacent side is what we're looking for. So algebraically, what's going to happen is really the tangent of the angle and the radius, they're going to trade places. And so I'm going to say the radius is equal to 12 divided by the tangent of 62. So the radius is about 6.381. Now again, I'm rounding that number for us to be able to write it down. Your calculator is going to display many more digits. We want to save that number so that we continue using it. You don't want to do your math with a rounded number, even though you wrote it down as a rounded number on your paper. Keep all of those digits, save it on your calculator so you can keep using it. Well, now that I know that the radius is about 6.4, I can substitute it into the volume formula. Now here it's really not going to be something that we can take the exact value of in terms of pi, because our radius is not going to be an exact number. We had to round it, or at some point we can't use the entire decimal numbers that the radius gives us. So in this case, it's not appropriate to try and get an exact value unless you want to keep everything like in terms of pi and in terms of tangent. But so just give me the exact or the approximate numbers for problems like these. So about 511.6 meters cubed. Now here, this is a composite shape. Here we're going to be trying to take the volume of two things. Either we're going to be combining them through addition or taking the difference of them through subtraction, depending on the shape that we have. In this case, we have a cylinder and we have a cone. So we're going to take the volume of both of those and add them together. So a cylinder and a cone added together. Taking the volume of a cylinder, pi r squared times h, area of the base times the height, and the volume of a cone, 1/3 pi r squared times h. We're going to take those values and substitute it into the equation. Now I really like the way that this has worked out. This is how I would work it out personally on my paper. I'm going to say the cylinder plus the cone, substitute their equations, then substitute their respective values. So now I'm going to simplify the area or the volume of the cylinder. So that would be essentially 9 times 7, which would give me 63 pi. Then 9 times 3 1/3 of that is 9 pi. So the volume of the cone. I always struggle so much keeping prisms, pyramids, cones, and cylinders straight when I'm trying to talk about them. So I apologize for stumbling over the cone there. But so now those are like terms, 63 pi and 9 pi. We can add those together. So the exact answer would be 72 pi cubic centimeters, and the approximate value would be about 226.2 cubic centimeters. Now at this point here, this is where you can go ahead and pause the video and work out the first two practice problems on your own. And when you're ready, go ahead and hit play and check your work with mine. Okay, so hopefully you've taken the time to work out these two problems on your own. Very straightforward, cut and dry here. Hello, Miss Berry. Thank you for the email. What we're going to be looking at here is just, can you identify the parts and substitute them correctly? So here we have 1/3 times the base times the height. In this case, the base, again, is going to be a regular hexagon. So evaluate, find the apothem of the hexagon using rules of special right triangles. So 4.5 radical 3 is the apothem. There's 6 sides. Each side is 9 units long. And the height of the pyramid is 15. So multiplying everything through, I'm going to get 607.5 radical 3 is the exact answer, or about 1052 for the approximate answer. So here again, like I explained a little while ago, they're giving you the slant height and not the height of the actual cone. So we're going to have to use not trigonometry, but the Pythagorean theorem to find that the height of the actual cone itself is 8 feet. So substituting those values, 1/3 pi times 6 squared times 8 gives us 96 pi cubic feet, or about 302 as an approximate answer for the volume here. Now at this point we have a couple more problems for you guys to practice. At this point, go ahead and pause the video again, work out these last two questions, and when you're done, come back and hit play and see if you got the right answers with what I have. Okay, ladies and gentlemen, hopefully we have our problems worked out. If you recognize what we're seeing in problem number 3, they're giving us an angle measurement and a diameter. So we can figure out that the diameter is going to be 7, or that the radius is going to be 7 rather, and we can use trigonometry to figure out what the height of the cone is going to be. So that's the first thing that we have to do, is what's the height of the cone. So in this case, we're wind up using tangent again, because the opposite side of the angle is the radius and the adjacent side is the height. That's what we're looking for. So tangent again, opposite and adjacent. Solving for the height in this case gives us a height of about 11.2 yards. Now that I know the height, I can go and find the volume. And again, I'm not even going to try to get an exact answer on one like this. Because the 11.202, that's definitely not where the numbers stopped. That continues on for a long time. So the volume is about 575 cubic yards, and I forgot my dimension on there, but yards cubed. So the last one here, the volume of the composite solid, we have a cube that is having a cone removed from it. So the cube minus the cone is what we're going to start off with. The volume of a cube is side cubed, and the volume of the cone, 1/3 pi r squared times the height. Substitute their respective values. The radius of the cone in this case is going to be half of the length of the side, because the length of the side of the cube is going to be the diameter of the circular base of the cone. And here we're going to get the exact answer would be 132.651 minus that 11.05425 pi. That is an exact answer, or the approximate volume is about 97.9 cubic meters. Now that's going to pretty much wrap it up here for volume. Volume, generally students do much better with volume than they do with surface area, but we can't really do one without the other. You're always going to do surface area and volume kind of conjointly together, or jointly, when we work these types of three-dimensional shapes out in a geometry class. But if you have any questions about anything that you've seen here, by all means, let me know. The biggest common mistake that I see students do when they're working with volumes of cones and pyramids is they forget the 1/3. So please make a note to yourself. Don't forget about the taking 1/3 of the volume when you're working with a pyramid or a cone. But until next time, guys, be good to each other and take care. And if you have any questions, by all means, let me know. All right. Bye-bye.